So what's the first thing I want to do?
Draw current path.
Yeah, draw my current path. So I got all my current coming out of my power supply. I have how much of my current is going to be going through M1. Just talking, don't look at the numbers. I have all, so what I'm trying to get at is, I got all of my current going through M1, right?
Yep.
So as we're talking to it through ourselves, we can kind of find out what's going on. So I got all my current going through M1. And then I'm going to come up to my, what do I call this little spot here? Current node. So I'm going to come up to my first current node. And some of the current is going to go split off through this way. That means I got the current of R1 going through here. And it's going to join in with that current node. So now, as I'm talking, I got some of my current, I got all my current running through M1, all my current going into this current node. Some of my current's going to split off going through R1. The remainder amount of my current, which means I have the amount of current going through R2 and R3, is going through my M3 meter. So I got the current of R2 plus R3 going into this current meter. Then that current is going to come up and it's going to split. The current of R2 is going to go up through here, and the remainder amount of current is going to go through M5 and M6 and up to R3. And that current is going to join in with this current. Now the current I have going through here is going to be the combination of R2 and R3. If I were to put a current meter in there, I would get the currents of R2 and R3 in there. And then the currents of R2 and R3 are going to come in, and it's going to join in with the currents of R1, which means that I have all my total current back going into my source. Okay, so when you're analyzing these circuits, especially when we get into solid state, you kind of want to know what's going on with my currents. All right, so now I got my current paths and polarities. Then what's my next step? Fill in what we know. So what do we know so far? Resistance. Okay, and our resistance for R2, what's that, 400 ohms?
That's R3.
Or for R3, I mean, R3 is 400 ohms.
R1 is 2.0 and not 2.2.
Oh, it's just 2, okay.
Yeah.
Okay, there we go, good, thanks. Remember, I'm looking at a very pixelated picture here, so when all I see, when I'm looking at this and I'm analyzing circuits, all I see is about this much of the whiteboard, so. All right, so then what else do we know about any of the circuit? Before we even use our calculator, what else do we know about some of this circuit?
M1.
M1, yeah, what's, so we know M1 is 100 milliamps, so it's also, M1 is also our what? Our total current. So we can put that, our total current in there. And our total current is going to be equal to 100 milliamps. Okay, what else do we know?
The current of M6.
Yeah, we know the current of M6, and where can I use that? On R3. Good, that's 50 milliamps. Yeah, now we can figure out our voltage because we got pretty much everything that we can write down there without using our calculator. So now we know, once we know two things, let's find the third and the fourth. So what's my voltage across R3 then? 20 volts? Okay. And since I'm working with parallel circuits and I found my voltage of one of my branches, what remains constant in a parallel circuit?
Voltage.
Voltage. So where can I use that voltage other places?
Everywhere.
Everywhere. So I'm going to put in 20 volts there, I'm going to put in 20 volts there, and I'm going to put in my 20 volts there. Look at how much we starting to fill in everything. All right, so now let's finish up R3. And what's my power going across R3? One watt. Okay? Then we might as well, then we can go ahead and do R2 because we know two things about that one. So we can find the third and the fourth. So what, how much current do we have going through R1 then? 40. What's my current going through R1? How much? 10 millivolts? Or 10 milliamps? Okay? And 10 milliamps going there. And then we might as well calculate out the power. So how much power do I have going through, going across, just being dissipated across R1?
$200 milliwatts.
200 milliwatts. Okay, good. Then we might as well find out everything for so what's my total resistance going to be? What's another way of calculating on total resistance? Using Ohm's law.
Voltage divided by current.
Yeah. So don't forget sometimes that some of our easy formulas are still applied. So we can figure out our total resistance of Vt over It. So my total resistance of this circuit is going to be what?
200 ohms.
Yeah, 200 ohms.
200 ohms. And when we're double checking our things, one thing about parallel circuits is that we always want to make sure that our total resistance is always going to be less than our smallest resistor. So when we're doing our double checking just for approximations, we know that we're going to have something less than 400 ohms for our total resistance. If you have something more than that, then you know you did something wrong. Because our total resistance is always going to be less than our smallest resistor. Alright, so then we got 200 ohms. We might as well finish it up. Then what's my power total going to be?
Watts.
2 watts. Okay. So now we still have to figure out the values for, we still only have one value for R2. We need to figure out the rest. Several different ways that we could do it. One way would be, like I talked about it earlier, we could go ahead and convert this into conductance. Get our conductance for this one, get our conductance from these two. Subtract these two conductance from this total conductance. And the remainder would be the conductance for this one, and then we just have to do the inverse and we can find the resistance. Or we can just go ahead and talk to ourselves about it. We know that we have how much current coming out of our power supply? 100 milliamps. So we got 100 milliamps coming through. Comes into our first current node, and how much of it's going to go through R1? 10 milliamps. So that means how much remainder do I have going through M3? 90. So I come into my first current node. I'm going to have some of my current, but we don't know how much. But I do know how much is going to be going through my resistor 3. So how much current would I have remaining going across here? If I know that I got 90 coming in, 50 of it's going to go this way, how much is going to have to go through R2? How much? 40. 40 milliamps. Now, we already identified two things. Now we can just use the calculator and figure out the rest. So what's going to be my resistance of R2? 500 ohms? And what was it? 800 milliwatts? Okay, now all we have to do is just figure out our meters. So I got all my current going through M1, which is 100 milliamps. Some of it's going to split up, and how much is going to go through M2? 10 milliamps. How much is going through M3? 90. It's just going to be 100 is going this way. 10 of it broke off, so the remainder is going to go through M3. So that's going to be 90 milliamps. And then M4, how much current do we have going through M4? 40 milliamps. And then, so 40 of it split up. The remainder amount of it was going through R3, and that was how much? 50 milliamps. And how much is going through M6? 50 milliamps. Okay? So now to double check our work, we know that these are current dividers, so if I add up all my currents, I take 10 plus 40 plus 50, I get my 100 milliamps. Check my power, if I add 200 milliwatts plus 800 milliwatts plus another 1 watt, I get my 2 watts. So everything's looking pretty good. Here I have to add my total resistance. What's my formula for total figuring out RT? Yeah, the inverse of R1 yep, and so on, yep. However many resistors you have in a parallel circuit. Okay? So when you're analyzing these circuits, just fill in everything you know, and then start talking to yourself and find out what's going on with your currents and stuff like that. Sometimes we have to convert them into conductance to find out what the last resistor is. But sometimes we can just kind of do it just by talking to ourselves and going through what's going on with our currents. But the current directions and the polarities and stuff, that's a big deal when we're working with solid state devices. We need to know that. And how much current we got going through our solid state devices. Alright? Alright, so one of the other formulas that's really nice to have, and we use parallel circuits all the time. So for example, let's say I have just going to have a single resistor here. We're going to say this thing, let's say we're going to say this is going to be, let's say it's 120 ohms, and it's putting off, let's just say it's putting off 500 milliwatts, okay? We don't care about the voltage or anything like that right now. So what we're doing is that I got this component that's going to dissipate 500 milliwatts of power. So I go over to my parts bin and I know that I need a 120 ohm resistor, and I go into my parts drawer and I got a whole bunch of 120 ohm resistors, but they're all quarter watts. Okay? Well, that won't take care of the 500 milliwatts. So a lot of times what we do, if we know that we need a total resistance of 120 ohms, what I can do is I can go ahead and I can add in, take two resistors. I could go ahead and take two 240 ohm resistors, if all I have is quarter watt resistors. Okay, so my total resistance of this circuit is, because now since I have two resistors the same, it works out really nice. All I have to do is find out what my RT is I just take my resistor value, so I'm going to say my 240 ohms, and I divide it by how many I have in my circuit. So if I have two 240 ohm resistors in parallel, I can just then divide it by 2. And what would be my total resistance then for this circuit then? How many? 120 ohms. Just like I had up here. Okay? It's the same circuit. I'm going to get the same currents and stuff. My current's going to divide up, so I divide up my current. All my current is going to come up, and it's going to divide. And since it divides up, my power cuts in half. So now I can go ahead and I can still dissipate my half a watt power going across my two resistors. My total resistance that I needed for that circuit anyways was 120 ohms. So now all I'm doing is I'm dividing up my power across those to dissipate that power across two of the resistors. So sometimes when we need to do that, we need to take a look and go, well, I need 500 milliwatts of power, but I only have quarter-watt resistors. So all I have to do is I just have to times that by 2, and then I can split it up, and I still get my 10, 12 amount of resistance. So this one we use a lot because when we're trying to divide up our current going through our resistors, we just divide by the number we need, and then we go into our parts bin, and we can just use our quarter-watt resistors, and we still get the same amount of power out of it. Still get our it still can handle our 500 milliwatts of power and stuff. But yet we're still loading that circuit down by 120 ohms. Okay? So that was another one. That's the next one. Is just remember that RT is equal to your, we'll just say R code divided by however many you have in the circuit. Okay? As long as they're all the same, we can just take that many number. So if I have 10 240 ohm resistors, I can just take 240 divided by 10, and that would give me my, what is that, 24 ohms? Whatever it would be, it would just come out to be that 24 ohms. I can just divide it by 10. So that's another nice little formula that we like to use. All right. All right, any questions on parallel circuits? Pretty straightforward. All right, we'll let you work on the rest of those. We're going to go back to our Chapter 4 worksheets now since we've worked with parallel circuits a little bit. There's a circuit in there on our Chapter 4 worksheets. So dig that one out. We want to make sure that we go over because this is a real common circuit that we use all the time.